Hello everybody, I want to start you with a very simple example of combined loading so you get some idea of how we handle these type of problems, and then I would have two problems that are a little bit more involved. So here we have this cantilever beam, as you could see here in this picture, subjected to three forces, a 600-pound axial load and two concentrated load of 480 pound acting over this cantilever beam at the distances shown here. By the way, this distance here, even though is not shown, that's 10 inches right here. Okay, so what we are trying to find here is we want to find, actually the objective is to find sigma and tau, normal stress and shear stress at these 3 points, points A, B, and C. Now point A and B and C are located at this right here, at this section, which I call it AA, right? And by the way, this is not obviously the most critical section of this beam. The most critical section of the beam is where that moment is maximum, and as you guys know, the moment is maximum always at the fixed support. Okay, but again, for the sake of doing a problem, we'll just look at a particular section and see how we can, actually look at the internal forces at that section and then try to, use those numbers to calculate our normal stress and shear stress. All right, so what I did here, I basically said, okay, let's look at this section. So if we cut right here and look at the left side of the beam, right? You could use also the right portion of the beam if you want, but it's easy actually to use the left side. All you have to do, guys, is to just transfer all the loads to that section. So take this 600 and put it right here. And that actually an axial load, which I call it N instead of P. It's like a normal force. Remember when we were doing internal forces, we had normal force, shear force, and bending moment. So that's why I'm using N here. Okay, the sum of the 480, the two 480, when they're transferred to this section, right, that becomes 480 plus 480, that's 960, and that's your shear load. Okay? So you put that right here. And then I also calculated the bending moment, the moment that these two 480 generate about that section. So you could see clearly that if you go ahead and find the moment, you have a 480 times this distance, which is 40 inches, right? And I have another 480, both of them are going in the same direction. Then this one is 10 inches, which I didn't have initially. But now when you add those two, that comes out to be an even 24,000 pound inch. Okay? So you put that bending moment and look how that moment acting. So you see, it puts point A here, point A on the top fiber of the beam in tension, but point B is going to be in compression. You see, it's pulling A out, but it's causing compression at point B. And look what happens at C actually. The stress due to bending, I didn't want A to be mixed up with uppercase A with the area here. Anyways, guys, so we have two types of stresses here. A stress due to axial load N, so that would be just load divided by area, right? So that's 600 pound divided by 24 inches squared, that's 25 psi. And then the other stress is due to bending moment, right? MC over I, right? That's 24,000 times, what is C? C is half of the depth, the distance from the neutral axis to the top fiber or bottom fiber, right? So that's 3 divided by the I that I calculated here for you, 72. So that comes out to be even 1,000. So this is the part that we do the combined loading. So why this looks a little bit different here. Let me just put the A back here. Okay, so sigma at A. You have to understand, guys, that when you look at this picture, you think that this N is only acting at C. No, you have to think of as if you are capped this depth of the beam, and the load is distributed evenly. So it's going to affect point A, B, and C the same way. So the effect of the normal force, the axial force, is the same for point A, point C, and for point B. Okay, that got erased too. All right. But now take a look at the moment about x-axis, the internal moment. As I showed you earlier, that causes point A to pull. So it would be in tension, so we add plus. And then, but for point B, that's going to be in compression, right? It's going to go in. So that's why we have negative. And then, of course, for point C, as I mentioned, point C is right on the neutral axis, and we know that the stress due to bending right on the neutral axis is equal to 0. So look, we have already the numbers here, right? 25 plus 1,000, that's 1,025 in tension. Just 25 psi due to this axial load here. And then the difference, 25 minus 1,000 minus 975. So that takes care of your normal stresses at A, B, and C. Let's go ahead and take a look at the shear stress. Now you guys remember from the chapter with the transverse shear stress that we have a shear load that I calculated in the previous page. Here it is, 960. I'm redrawing it over here. Now you guys remember that how this the stress changes parabolically like that, and this is point A, so tau at A is 0. That's why I have tau at A 0 here, and tau at B is also 0, right? And tau at C is, this is point C, becomes maximum, right? Parabolically like that. So, and by the way, do we have to use the VQ over IT? No, don't have to. We know that if you have a solid rectangle, which is the case here, we could use this, 3/2 V over A. So 3/2 of what? 960 divided by area. That comes out to be 60 psi. So the last thing I want to show you is a stress element for each point. So this stress element will show us what stresses are acting. You could think of it as a two-dimensional or a three-dimensional cube, by the way, it doesn't matter. If you look at it as a two-dimension, you could see that so point A is what? Right on the top fiber, point B is right on the bottom fiber, and point C is right in the middle, right on the neutral axis with the centroid line. Okay, so you could see that point A is in tension, right? 1025. Point B is in compression, 975 psi. There is no shear stresses, remember, at A or B due to what? Transverse shear stress. So no shear stresses around this or around this. But at C, we only have a stress due to the normal axial load, and then but we have shear stresses. How did I figure out the direction of this guy like that? Basically, you just look at this, the way this shear load acting. So it's going down. So right at that point, you could say, or you could see it actually in this picture. You see how this shear load is acting down. So at point C, see this shear load is acting down. So at point C, that would be downward direction. So once you figure out the direction here, you know the direction should be up, to the left, and to the right, because remember that once you figure out the shear stress on one face, the shear stress on the other three faces should be exactly the same. By the way, if you want a three-dimensional stress element for this, it would look like this, by the way. This is for point C, of course. So you have just a very small axial stress. And you could actually label these and give it, sigma x, sigma y, whatever you call your axis. And we'll look at that in the other examples. And then the shear stress going around, you could see there would be a shear stress in this face, a shear stress in this face, a shear stress up on this face, and a shear stress like that on this face. And they're equal to what? 60 psi. And this one actually is also 25 psi. Goes without saying that we have also 1025 and 975 psi. Okay, this was a very trivial problem that I'm trying to show you. I want to actually show you some examples with the circular cross sections in particular, because you see in this particular problem we didn't have any shear stress due to twisting. You see, we had normal stress due to what? Axial load, and normal stress due to bending. So we could, combine them and add them up or subtract them in this case. But we didn't have this guy, the TC over J. If we had a circular section, then I could show you how this TC over J gets combined with like VQ over IT, or the 4/3 V over A if it's a solid rectangle, a solid circle rather. Okay, so I'll be back with more examples hopefully of combined loading, and as always, thanks for watching and listening.